Hello friends, welcome to my YouTube channel. In this video, we present a very simple proof of a famous result from the theory of sets and functions, which is popularly known as Schroder-Bernstein Theorem. We begin with the presumption that all our viewers are familiar with the basic terminologies used in the theory of sets and functions. So let us now straightway go to the statement of Schroder-Bernstein theorem, which says that if x and y are two sets such that there is an injective function f from x to y. Injective function means 1 function. Okay, distinct elements go to distinct elements. And also there is an injective function g from y to x. Then there is a bijective function h from x onto y. So if there is an injective function from x to y, if there is an injective function from y to x, then there is a bijective function h from x onto y. So let us now prove it. Let us first define a sequence Zn n running over natural numbers 1, 2, 3, 4 and so on. This is a sequence of subsets of y, that means each Zn is a subset of y, and this sequence is defined iteratively by setting, first of all we define Z1. So the first element of this sequence is complement of fx in y, that means it is y minus fx, and all other elements are defined by this formula, that is next element is defined by applying this composite f composite g. F composite g means first you apply g and then apply f. So it is actually a mapping from y to itself. Okay, g goes from y to x and then f goes from x to y. So f composite g is a mapping from function from y to y to itself. So apply this composite on zn minus 1 for all n greater than 1. So that means n is at least 2. So you will apply first you will apply on z1, that will give you z2. Then apply on z2, you will get z3. So in this way zn is equal to f composite g applied on the previous element. So every element of this sequence is obtained by applying f composite g on the previous element, previous term, and the first term is defined by this. So this sequence we consider defined in this manner. Okay. Next, we note that this Zn, actually these are subsets of fx. These are all contained in fx for all n greater than 1. That means except n equal to 1, except n equal to 1, which is actually complement of fx. So no chance of it being contained in fx. So z1 is not contained in fx, it is actually complement of fx in y. But what about the other zn's? So z2, z3, z4 and so on, you can see from here it is actually lies in the image of f. So g, first you apply g and then apply f. So everything here is actually in the image of f. So that is what is written here, that this Zn is contained in fx for all n greater than 1. Therefore, this Z1, since it is complement of fx and these are all contained in fx, so this Z1 will not have any common element with this union. union going from 2 to infinity, okay, n greater than 1. So n running from 2 to infinity. So in this union, there will be no element of Z1. Z1 will have nothing common with this union, okay. Reason is all these Zns are contained in Fx and Z1 is actually complement of Fx. Consider now the set Z, which is actually union of all the Zn including Z1. So here n is running from 1 to infinity, 1, 2, 3 and so on. Okay, so see the difference here. In this union we are considering n greater than 1, but here we are considering n starting from 1. Okay, and this is of course a subset of y. Everything we are considering subsets of y only. So okay, now what about the complement of z in y? So what is y minus z? Now see, this is contained in y minus z1. Why? Because z1 is actually a one of the member here is z1. So z1 is actually contained in this union. So z1 is contained in z. So z1 is contained in z. So if you subtract a bigger element, it will be contained in, if you subtract a smaller element. Okay. So y minus z is contained in y minus z1 because z1 is contained in z. And what about y minus z1? Z1 is actually complement of fx in y. So complement of z1 will be precisely equal to fx. So what we see from here is that this y minus z is actually contained in fx. So it follows that this y minus z is actually equal to fx minus g. So y minus z is contained in fx. Okay. So if you subtract z from both side, here it's already subtracted and here it will be minus z, and since nothing from z is contained here, so even if you subtract or don't subtract z, it will not make any difference. Therefore this left hand side will be contained in right hand side. And on the other way, what happens? Fx is already contained in y. So fx minus z will be contained in y minus z. So that is how these two are actually equal. Okay. So y minus z contained in fx actually gives you this equality. Okay. Our fx is already contained in y, so we get equality. Also note that this z minus z1. Now z is this one. It z1 is included here, but z1 has nothing common with rest of the zns. Therefore, from this z, if you remove z1, the rest of the elements will remain only. So z minus z1 is actually precisely equal to this union of zn where n is greater than 1. Okay, because this intersection is empty. So from z, if you remove z1, you are actually not removing any element of this union. So it will remain as it is. So this is one observation. Now consider the set W equal to image of z under G. So our z is this one and W is the image of z. Z is a subset of y. So apply small g, the function g on z. The image of this z under the function g, we call it W. So W equal to z g of z. Then apply f on W. What is f of W? It will be f of g of z. That means f composite g of z. And f composite z of g is equal to, you now put the value of z. Z is actually union of all the zn. So if you put the value of z here, it will be like this, n going from 1 to infinity. And now these maps are well behaved with unions, arbitrary unions, so it will go inside. So it is f0, f composite g of zn, and union comes outside. And from the definition of zn plus 1 and all, this is actually equal to zn plus 1. Okay, we have defined our zn iteratively by applying f composite g on each term, we get the next term. So if you apply F composite G on Zn, you will get Zn minus 1. So this union is going from n is going from 1 to 1, but practically the suffix of Z, if you see, it is going from 2 to infinity, 2, 3, 4. Okay, n plus 1 is not equal to 1. It is always greater than 1. Therefore, this union is actually equal to this union. You can write it as Zn where n is strictly greater than 1. Okay, so this union is same as this union. And this union we have seen to be equal to Z minus Z1 in our previous slide. So this union, it is equal to the whole of Z minus the first element, that is first term of that sequence Z1. So this we have seen. So what does it mean? It means that f of W is equal to Z of Z minus Z1. Alright. Therefore, since f is an injective function and also since z1 intersection fx, z1 is complement of fx in y, so this is empty, and f is injective given, f is 1 1, it follows that what is the image of complement of w in x under the function f? What is f of x minus w? Okay, w is the image of z under the function g. It is a subset of x. Look at the complement of w in x and apply f. So what is this image? This image is actually equal to fx minus f of w. Why? In general, this equality doesn't hold. But then here we have f is 1 1. F is injective. So here it is given that f is injective, right? Therefore, this equality holds. F of x minus w equal to fx minus f of w. And this is equal to f of w we have seen equal to z minus z1 in our previous slide. Image of f is actually precisely equal to z minus z1. So this is equal to f of x minus z minus z1. Now z1 has nothing common with fx. z1 intersection fx is empty. So whether you subtract z1 from here or don't subtract from here, it makes no difference. Therefore, this is actually equal to fx minus z, because z1 has nothing common with fx. So even if you don't subtract z1, that will not make any difference. So this is actually equal to this one. So what we have seen here, that this fx minus z we have already seen in our previous slide, that this is equal to y minus z. Therefore, the image of x minus w under f is actually equal to y minus z. Okay, we have already seen earlier that this y minus z is contained in fx, so it is actually equal to this one. Okay, so fx minus z is equal to y minus z, that we have already seen. So if you want to see it again, let's go back a little bit. So this is f of w equal to z1, we have used this one, and then we have used, yeah, this is the one, y minus z is equal to fx minus z. Okay, so this we have used, then this we have used, and then we have used this one. All right. So what does it mean then? It means that this x minus w is actually bijective to y minus z under the map f. Okay, more precisely under the restriction function f restricted to x minus w. Okay, so what does it mean? F of x minus f is already given to be 1 1 injective, and y minus z is the image of this set under f. So this particular set here is bijective to this particular set here under the map f. All right. So that's what we are mentioning. So therefore, this means that the restriction function f, if you restrict f on x minus w, it is actually a bijection from x minus w onto y minus z. So these two are bijective, and under this bijective function f restricted to this set. Okay. Also from the definition of w, what is w? W is actually image of z under the function g. So w equal to gz, g of z. So that means this restriction function g restricted to z is actually a bijection from z to w in the opposite direction, from z to w. Okay. Okay, because g of z, g is again 1 1, g is also given to be 1 1, and this w is the image of z under g. Therefore this z and w are bijective to each other under this bijection. Okay, that is the inverse. Now this, since it is a bijection, we can talk about the inverse function. The inverse of g restricted to z, this is actually a bijection from w to z. So what we see from here, f is a bijection from x minus w to y minus z, and this is a bijection from w to z. So from w to z we have a bijection, and from complement of w to complement of z we also have a bijection. So we are actually done. So therefore we have a bijection from whole of x to whole of y. Whole of x is actually equal to complement of w union, disjoint union w. These are actually two disjoint sets. Their union is x, and y is a disjoint union of these two sets. These two are also disjoint sets. Complement of z in y and z. And we have just now observed that, this is a bijection from this to this. Okay. So from this to this we have a bijection that is given by this. Okay, this is given by this f, and from w to z also we have a bijection. Okay, and this is given by this. That means here it is given by this. All right. So we have a bijection from whole of x to whole of y, and if you want to see its actual definition, it is actually defined by this: hx equal to, if x belongs to the complement of w, it is the image of x under f, or more precisely image of x under this restriction function. And if x belongs to w, then it is the image of x under this inverse map. Okay, g restricted to z inverse. Okay, so this also exists. This is also a bijection we have seen in the previous slide. So h is actually defined like this. Okay, so in this way we have a bijection from x to y, and this completes the proof. Hope you have enjoyed this video, and thanks for watching.